So we're going to get started with our session. So people are outside, if they want to come, grab your water.
This is the best. I don't know why you skipped this. I thought this was what LSST was for. I did.
Okay.
Yeah.
That's
Now I found that it's mostly for asteroids.
all right. So before we get started, there's some reminders for everyone. In case you want to let people know about any unprofessional conduct, please contact the RCW Code of Conduct contacts here. And we have strict regulations on the COVID-19 policy. So if you see these stickers, please respect their stickers. And yeah, just a reminder for online participants, please stay muted unless you're asked to speak. And in-room participants should speak in the room microphone, which we just have one. So I'll be running around and handling that with you guys. So before we get started with the first speaker for the session, I wanted to give you a brief highlight what the Rubin AGN Science collaboration is all about. So you must have heard from Neil a couple of days ago, yesterday actually in the plenary session. The AGN Science collaboration currently is 325 plus members strong. We have a lot of participation across the globe. And as you can see here, there's a lot of participation from the US and consistently rising participation from the European side, as well as representation from all across the world. Talking about the working groups and active task forces, we currently have 4 active working groups. The classification group led by Gordon Riches and Neil Brandt, variability group led by Amy Segunda and Wei-Zhang Yu, Photo Z by Rafael Shirley and Roberto Asif, follow-up surveys by Bindu Rani, who's here in person, and Claudia Ricci. Apart from the core working groups, we do have a lot of ongoing and active task forces. Some of them are highlighted here. The watchlist task force that liaisons with the alert brokers in order to anticipate any new and upcoming unknowns AGN kind of objects. There's the periodicity task force, and effectively we also have a couple of more listed down here on the right. There have been a lot of featured researches and publications recently after the charter of the AGN Science collaboration was set. So here I'm highlighting a couple of them, which Neil also did in his presentation yesterday. And effectively, we are spanning all across machine learning, time delay measurements, accretion reverberation mapping, and effectively also trying to get photo Zs and understanding scalable and robust multivariate modeling using pipelines. Also, we have ongoing data challenges in pipelines. This is something open to all. The entire collaboration is actively participating in them. The 2 that are consistently going on right now is the AGN reverberation mapping project, as well as the supermassive black hole binaries and periodicity challenge. So the results for the first one have been actually being tabulated. The entire collaboration did a lot of work on this, and we are trying to wrap up having a APG supplement paper ready out of that. We also do yearly summer meetings, and this has been ongoing since 2018, pre-COVID era. So these are some snapshots from the recent one, the last 4 activities. As you can see, the locations keep on changing. So we have vibrant participation from every corner of the world, and with researchers young as bachelors and undergrads and senior professors included. And finally, I just wanted to open this up for collaborations. So people who are interested and new to this, please apply. Please go to the website agn.science.lsst.org, and you could find all the information about the past activities the collaboration has been doing, members that you want to reach out, and also apply to join the collaborations. So without further ado, I will now call Bindu Rani, who's going to be the first speaker of the talk. I'm just gonna. So Bindu is going to talk about LSST agent follow-up, key developments, and activities.
Welcome everybody. I'm Bindu Rani. I work at NASA Goddard Space Flight Center. I'm talking about some of the exciting and new science we will be discovering with Rubin observation. So, can you guys hear me okay? Especially that side, okay. So Rubin will transform the way we study AGN. And because of that, we have both opportunities and challenges. And if we are managed to understand the challenges, I think there will be even more opportunities for us to understand AGN in a better way and on larger scales. In my talk, I will be basically talking about most of the recent activities where the multi-wavelength follow-up group is focused on to increase the science return of LSST observations. So, as we know that Rubin will observe about more than millions of sources in a single night. And there will be more than 1 million AGN that we will be seeing every single night with Rubin. And this means we have a huge data. We have huge data to work on, and there will be new parameter space. There will be a revolution in the time domain astronomy, and it will be opening many new parameter spaces of discoveries because there will be many more new transients, and there will be many more different classes of sources that we will discover with Rubin. And to meet the data challenges and to achieve the science goals, we have a very active collaboration, as Sam mentioned about the collaboration. So I think I'm gonna skip this slide. So we have task forces which are designed to focus on key areas, and the task forces are designed in a way that some of the task forces are focusing mainly on Rubin only observations. What can we learn with Rubin only observations, and what can we learn with immediate Rubin observation for which we don't need longer time domain observations. And then there are task forces which are focusing on coordinated multi-wavelength observations. And the idea is to develop and coordinate follow-up strategies so that we have a win-win situation for us too and for other observatories too. When it comes to multi-wavelength and follow-up or multi-wavelength observations, we have a huge challenge here. And why? Because if you talk about Rubin, the amount of sources Rubin will be seeing, they will be like in millions. If you talk about other observatories, the number of sources a given observatory sees in a single day or night, it's of the order of thousands. So here I have an example, the Swift X UBOT observatory. It sees about 4 to 60 observations in a single day. And given that, and we have the similar case for other observatories too. So given that out of those 1 million sources, which 4 to 10 sources we want to focus on that particular night? So we have to come up with a really, really tight criteria so that we do not miss the opportunities like we had in the past for a gravitational wave event or the neutrino event, or there may be other transients which have a huge science return. And we also want to make sure that those sources, they are visible by Rubin and by other observatories too. The time sensitivity, time coverage, how immediate rapid follow-up observations we need, that's also important. And then we need to establish a coordination between different observatories so that the researchers, as we know that astronomy, if you compare to other science areas, it's a small, fraction of the researchers. So we want to make sure that we don't need to spend too much time in coordinating those observations. There are channels available where people can just, hey, this is important, here is why it is important, and it goes through the pipeline. So this is something we are working together as a team. And what facilities are we focusing on? We are currently focusing on facilities in high energies, radio, optical, infrared. wavelengths. This includes most of the known ground-based and space-based observatories. So in the following slides, I'll be giving one or two key examples for each science case. And I apologize if your favorite science case is not here in my slides because I only have 15 minutes. But there may be way more science topics beyond my slides. And I'm sure other people will be talking about the other science cases as well. So one thing I want to start with, what we will be having, simply forget about the other observatories. Simply with Rubin, we will have millions of well-sampled light curves in different optical wavebands. And what we can achieve using only these light curves, that's one key science that is really important for us. So with that, what we can learn is that we can learn in many, except from the jetted AGN, where the emission is coming from the jet. Most of the optical UV variability we see from these sources, it's coming from the central region of that AGN, or if you are or central region around the black hole. So in that case, if we have these multiple multi-band beautifully sampled light curve, then we can use the reverberation mapping tool to study the structures, how it evolves, and what is its relation to the black hole mass itself. And this study can be performed for different kind of AGN and for different black hole masses. As you may have heard about, there are dwarf galaxies as well. And, science is universal. So we never know, like the same physics applies to all the sources, or there might be different factors dominating in one kind of population compared to others. Another example, studying supermassive black hole over the cosmological evolution. As you can see that there are a handful, even with JWST, we still know a handful of sources at higher redshift. With Rubin, if you take a look here at this plot, we will be seeing more than about 50 sources at redshift higher than 7. And this is just simulated result. We never know what the future holds for us with Roman and Rubin observations. So observatories, we will be seeing a lot more high redshift sources. And studying these sources at high redshift, it has a really high impact on understanding how the black holes evolve, how black holes were formed and evolved over the cosmic time. Another example, AGN, as we know that now AGN are AGN are multi-messenger sources, and they are prime targets for neutrino follow-up observations too. So following those sources, it has a high science written as well. And another thing here with Rubin observations alone is to identify the binary candidates using the time domain observations. For that, we need multi-band light curve or even a single band light curve, but observed over long duration of time. So we might expect to identify more than hundreds of these sources over the Rubin time period. Speaking, another example is the okay, so this is again binary. I think I covered that. So let's talk about a little bit about the rare and transient phenomena, which has a huge science return. And the reason is because we don't know what those sources are. The transient brings new physics, new kind of exotic science that may follow our standard AGN models, and they may completely challenge that. Anyway, it's important and it's essential to understand those sources too. So there is a task force which is transient task force, and it's looking at these rare and exotic phenomena, and they have identified the observatories, and they are working on the proposals so that these cases can be followed up in detail by multi-wavelength observatories. AGN watch list, which SWAM and others are leading, and I think they are coordinating with all of us. And we meet on regular basis so that we can provide feedback to each other. And the idea is to come up with a list of sources and to come up with properties of those sources, so that if there is a new candidate, then we can easily identify it on the basis of those properties, and it's easy to follow up that particular candidate. Blazar Task Force is mainly focusing on the Blazar science, which includes studying Blazar population across different redshifts. I'm sure Ruben will be seeing a lot more Blazars than we currently know. Another key focus of the Blazar task force is the neutrino follow-up. Blazar, as we know, they have jet, and jet can accelerate particles to higher energies. And if the emission mechanisms are hadronic, then neutrinos are a natural product. So given that, they are prime candidates for neutrino follow-up. And in that sense, Blazar task force is especially paying attention to those sources. So I'm not sure how many minutes we have, but I'm kind of done. Okay, so I have 2 more slides, but there is one thing I wanted to focus on is the fact that we are very friendly people, and we like to collaborate, and there is opportunity for everyone. And if you want to get involved, if there is a key science area which you feel like, okay, look, Ruben might be discovering this particular kind of sources, and I think that there should be a task force for these particular science case as well. Then you're welcome to contribute that way, and there is always opportunity to have to initiate new task forces and to lead that. And if you want to do that, where did my? I think I have one more slide where I have the link where you can click and you can apply for AGN Science Collaboration membership, which, okay, it looks like this is my last slide, but did you have that link in your slides?
Yes, I can add it to the slide.
Okay, thank you. Yeah. So everybody is welcome to join if you're not currently a member of the AGN Science Collaboration. And by the way, one person can be a part of multiple science collaborations too. If you are working with Galaxy Group and you think like, oh, my expertise match with AGN Science Collaboration as well, you're welcome to join. And I would be happy to take questions. I had 2 more slides, one link, and then thank you.
Okay. That's time to do again. Keeping adjusted with the time, probably we'll take the questions together. So if you have any burning questions, there is threads on the Slack. So please feel free to add your questions, and we'll have more time if you permit. Thank you. Moving on to the next speaker, we have Madison. She's going to talk about expanding the census of changing location of galaxies in the era of freedom of speech.
All right. Well, hello, everybody. My name is Maddie Reich. I'm a rising 3rd-year graduate student at Penn State University working under Professor Charlotte Ward on studies of changing like AGN host galaxies. So today I'm going to be specifically talking about how we're hoping to expand the census of changing like AGN host galaxies in the era of Rubin Observatory in joint with other surveys we've got going on. So just kind of first to start out with reminding everybody in the room what a changing like AGN is. A changing like AGN is an AGN that has exhibited the appearance or disappearance of broad emission lines. This is going from the type 1 obscured state, unobscured state, apologies, to a type 2 obscured state and vice versa under the AGN unification scheme. So we think that this spectral change is likely due to a variable accretion rate in the center supermassive black hole system. And there are many theories for why this variable accretion rate could be happening. One is maybe there's a small scale disk instability, like a disk tear, or there's also a possibility of an orbiting companion destructing something down on the scale of the accretion disk. So there are a lot of theories, and we want to try to be able to narrow down the pool of options. So we want to look at the host galaxy population of changing like AGN. Specifically, previous host galaxies populations of changing like AGN studies have been done, and they've revealed preferences for showing up in the green valley in between the active spiral galaxies that are actively star forming and the red dead ellipticals. They've also showed preferences for having disturbed galaxy morphologies, evidence of kind of this post-merger system. So we think all of these characteristics kind of give us an idea that this could be indicative of episodic accretion happening that's causing the changing look event. And this could be associated with periods of quenching or large-scale galaxy transitions. So this is kind of the current state, and here is an example from Charlton et al. Of one of these current or previous population studies where you see a very disturbed galaxy morphology. And what we want to just kind of mention is we have very small samples of well-resolved, well-characterized changing look AGN host galaxies on the order of 20 or so. And these are all kind of dependent on multi-component Sursic models to fit the extended and disturbed galaxy morphologies. So we don't really want to rely on parametric fits. If possible, we want to use non-parametric galaxy fits. So this is something that we want to do in the era of Euclid and Rubin, is fitting, first of all, scaling up our population of well-resolved and well-characterized host galaxies of changing look AGN, and also using non-parametric galaxy models. So again, we want to do this with Rubin, specifically using Rubin and Euclid in tandem. So we'll have the high resolution of a space-based observatory in Euclid, which will give us accurate galaxy morphologies and allow us to see and resolve the complex galaxy substructures. But then we want to use this in joint with Rubin Observatory with the deep multiband imaging that it will provide us. And so you can see here in this, on the right here, is kind of the overlapping footprint of Rubin and Euclid that we will expect as Euclid starts giving us data releases. Right now we're a little bit limited in that we have Euclid Q1, which covers deep drilling fields of Euclid Deep Drilling Field South and the Fornax one. So we've got a small region right now where we can look for changing look AGN, but eventually that region will, that sky coverage will increase in time. So here's kind of an example of the same field of view covered in Rubin Z-band coad and Euclid Visband. And so you can really see the difference in the PSF size, of course. And so what we want to be able to do is to use the high resolution of Euclid to be able to separate out different sources, because we'll expect as Rubin coads grow and deeper, we'll have a lot of galaxy blending going on, and we want to be able to separate that out. So we'll use the high resolution of Euclid to inform our fits, but also including the deep coads of Rubin. So how are we going to do this? We want to use Scarlet 2, which is a multi-resolution modeling software. If you were at the external synergy session earlier in this week, you heard Professor Charlotte Ward talk about it a little bit in more depth. I'm going to talk about how I could possibly use it here, but there are plenty of Scarlet 2 users in the audience and at this conference if you want to get more details. So Scarlet 2 gives us a GPU compatible, so we're able to scale up to the loads of data that we're expecting from Rubin. It gives us the non-parametric galaxy fitting that I discussed earlier that we wanted to be able to expand beyond relying on a multi-component Sursic model to fit these disturbed galaxies. And then it gives us the joint pixel processing of 2 different resolution images. So this will be able to allow us to take the Euclid image with the high resolution and inform our Rubin images to be able to separate out different sources that we care about. So here's an example of maybe this will convince you why we would want to use Rubin and Euclid in tandem. So the top row shows output galaxy morphology models from Scarlet 2 when we use both Rubin and Euclid information. So you're able to see, hopefully, there's more wispy extended structures that we're able to resolve and see in the galaxy morphology models that we don't quite get when we have Rubin imaging only. So, but while we're waiting, right now we again only have Euclid Q1 that's got overlapping regions with Rubin. So we're kind of waiting for Euclid data release 1 to give us a little bit more coverage so we can start trying to get at changing look AGN host galaxies from. So in the meantime, I still want to build the galaxy morphology modeling pipeline with Scarlet 2. And to do this, we're using the legacy survey imagings from DESI. So this gives us very wide field coverage in the Northern Hemisphere, and it'll give us 3 optical bands, G, R, and Z, made up of 3 different ground-based surveys of DECALS, which is the Dark Energy Camera Legacy Survey, MZLS, which is the Mayall Z-band legacy survey, and BAS, which is the Beijing, Arizona Sky Survey. So we have all of these giving us some depth and some playing ground to work with while we're waiting. And so here's one example passing through a turnoff AGN from Charlton et al. That I've showed before in the slide. You can kind of see it's got extended ring-like structure on the outside, so we don't quite get that with the resolution of legacy survey imaging. But here's an example of folding it through Scarlet 2. You can see our output residuals are all right. And this is the output Scarlet 2 morphology model that you get from this changing like AGN. So this is just one case of, hey, we've got the pipeline start to finish. So what do we kind of want to do with these output morphology models? Well, we're starting off by just kind of getting some precursor information about what do the pixel level morphology statistics of changing like AGN hosts look like compared to a control sample of AGN hosts. So we're going to start with a sample of 3,000 control sample AGN from Birmingham et al., which is well matched in redshift to the DESI selected 561 changing look AGN from Guo et al. And so this will have great overlap, obviously, with our DESI legacy survey imaging. So what we want to do is run through our pipeline, extract morphology models from Scarlet 2, and just compare some basic pixel level statistics. So there's kind of your traditional concentration, asymmetry, and clumpiness type metric. And there's also maybe some more recent studies of the egg metric, which is incredible. But so this covers entropy, Gini coefficient, second gradient moment, and these can be a more robust morphology statistic than the typical concentration, et cetera, because it doesn't necessarily rely on, like for concentration, for instance, relies on your center pixel being the brightest at the center. But so Gini coefficient probes a similar concentration type metric, except it allows for the brightest pixel to not be in the center. So that's just an example. And if you want to know a little bit more about how the egg morphology statistics are able to separate out different hosts and different galaxy types, you should talk to an undergrad in Charlotte's group. RJ Dunlap is here. He's got a poster. I don't know if the posters are still up or not, but you can always talk to him. He's been doing some interesting stuff with machine learning clustering and trying to figure out how these morphology statistics are able to separate out different populations. Yeah. So I also had one more slide, but it was just a summary slide, so it's probably okay. I hope I've convinced you that changing like AGN host census is going to be very well expanded by in the era of Rubin Observatory. I'm waiting for Euclid DR1, hopefully partially this fall. Yeah, we're going to use Scarlet 2. Scarlet 2, there's a lot of people in here that know about it, and if you would like to also do some joint image analysis of your space-based and ground-based observatories, you should come talk to any of us. And yeah, I'm happy to take any questions now. Sorry about my summary slide.
Time for one quick question.
Thank you very much for a very nice and clear talk. I have a question that might or might not be related to exactly your work. Do you know if there's a correlation between the changing look and the X-ray properties of those sources, and if that has been studied or not yet?
That's a good question. I haven't looked too much into the X-ray properties myself, but I know that there's another kind of way to get at the changing look phenomenon that's maybe closer to, I believe, instead of a changing accretion rate, kind of what we think being the cause, it's more of a change in obscuration, possibly, that's causing the X-ray variability. Yes. I haven't gotten too much into the weeds of the X-ray side of it, but yeah.
The same answer again. And our next speaker is going to be me. Hello, everyone. So my name is Swayam Truptapanda. Today, I'm presenting a work that's been led by one of the undergrad students that worked with me as an intern at Gemini Observatory. And it's been very well set right now with the talks by Bindu and by Madison, effectively. So what I'm going to show you is the largest compilation ever of a changing look database. That's sort of a long time coming. We do have a lot of work that people have done over the years, getting a lot of samples from different surveys and doing homogeneous studies, but we still lacked a sort of an infrastructure to bring it all together, since we are now talking about tens and millions of AGNs as we go along. And not only this database serves itself as a template in order to identify new targets, but of course, you'll be also monitoring the same targets over a longer period of baseline. So Mariangela is just finishing her master's degree right now, and she's going to soon search for a PhD, so please look out for her application. She's a fantastic person and really did a great amount of work getting this compilation together. So a quick background, I don't really need to tell people here, most of them are already aware of what AGNs are and what a changing look AGN is, but just giving a sort of brief timeline history of what's the status of the topic of the objects that we're talking about. Starting from 1970s and 90s, we had this individual discoveries where effectively we started knowing objects one by one on a case-by-case basis that changing look behavior starts to appear in isolated cases. So early reports go back to these papers by Tollin and Osterbrock, 1976. And then slowly we started making more efforts toward well-studied nearby objects such as the NGC 4151 and individual changing state systems. Onwards of the new decade and since the 2010s, what we call as the modern changing look era, the field has accelerated tons in terms of individual high-profile sources and repeat spectroscopy from different instruments. So there's a lot of work. I'm citing some of the seminal work that's been done in the last decade, which have tried to establish CL AGNs, the changing look AGNs, as genuine accretion state transitions candidates and not merely oddball single object curiosities. Starting 2018, we have been doing a little bit more systematically these searches from the SDSS, BOSS, eBOSS, and effectively after that, the DESI, where we are getting a lot more repeat spectroscopy and simultaneous time domain photometry, which has enabled to get larger and larger samples. There are a lot of works that have been doing this, and now we have entered into a phase from getting discovery papers to population size studies with knowledge about turn-on, turn-off classifications, and trying to understand actually what leads to the phenomena of changing look AGNs at the heart of the question. Now, going a little bit forward, now we have already entered the catalog era from the tasks and catalogs done to the BAS survey, the BAT analysis by Matthew Temple from 2023, from Grisha Zelton and the SDSS5 group in 24, and Wei Zhangguo's work from DESI, where we have actually accumulated a large number of objects that have been quantified as changing look AGNs or being classified as candidate changing look AGNs. So both with spectroscopically confirmed cases and photometrically selected sample candidates. So effectively, what the current state is right now is that the classification still remains quite heterogeneous. We are unable to really find out a kind of common ground in order to ingest all of these together so that it will be actually helpful for the community in order moving forward to such large surveys like the Rubin. So a couple of works that kind of are coexisting right now at this current era is the CLASS Plus, which is the S Plus, the Southern Photometric Survey on Cerro Tololo, where they have actually combined the information from single epoch photometry and taken information from spectroscopically derived objects from DESI and got a larger sample ingested using DESI and SDSS follow-up spectroscopy. And now as we enter the Rubin era, there are a couple of questions that we really want to answer. There are the expected population explosion that's going to happen, but how do we precisely and securely select candidates where these are either changing look types or maybe an unknown, which we have not even seen in the past surveys. So in order to kind of get started with that, we wanted to understand what's the survey and the studies that have been done till date. So we have all these rare Seifert anomalies, and moving on to the cases where multiple photometric and spectroscopic surveys have actually put efforts and tried to collect these sort of heterogeneous smaller samples. So we have already seen things from SDSS, from the Catalina survey, PanSTARRS, TESS did more of the high cadence transit light curves, Assassin, Gaia, ZTF has been the throughput thing before Rubin, and most of our studies have been based on ZTF discovery in order to train our algorithms in order to get ready for Rubin, and also SphereX, which has been doing fantastic in terms of its multi-band coverage. Also, we are in this era where right now we are not alone with single instruments or facilities. This is one example, one very nice thing that the DESI observations have led of hundreds of Rubin alerts. So the moment we started sending alerts in February, we have already been doing spectroscopic follow-up with DESI's Spare Fiber program, and we have got up to 61 sources rapidly classified across these two fields, mostly in those first coming fields from the Cosmos and XMMLSS. 5 new supernovas were confirmed and were reported to the TNS, and multiple known AGNs were also detected from these first alerts. So the idea right now for our catalog, the idea that we wanted to do is the homogeneous compilation, is to take this entire sample of data sets that we have at play from all these high cadence wide field time domain capabilities that are going to be run by Vera Rubin Observatory, and connect with this modern known knowledge of changing look AGNs. And effectively, by getting this sample out, we'll be able to match it with the footprint of Rubin and try to identify already existing sources that were known changing look confirmed candidates or confirmed sources itself. So this is a quick view of the multi-survey synergy workflow. So we go with the construction, very naive setup where we pretty much did a little bit of a hard task of looking through NASA ADS through keywords across 5 decades, and effectively got all the compilations, single objects, multiple catalogs, and individual source discovery objects, and try to compile this massive database altogether. So we also processed this through cleaning and homogenization, effectively removing a lot of duplicates, because a lot of works have been repeatedly observing single targets, but we don't throw it all away. We're keeping the MJDs and their epochs in order to identify whether newer epochs were actually ingested for the same objects. And by really getting the uniform coordinate system, we're able to consolidate the information of whatever is provided, spectroscopic, photometric information, or type change of changing look AGNs itself. At present, we have a master catalog of 38 changing look AGNs. And this is then, I'm going to show you how it relies upon the wide files deep and the DDF Rubin footprints itself. Effectively, a quick view of the results. There are 70 changing look AGNs already within the Rubin main survey footprint, of which 5 changing look AGNs are within the deep drilling fields, 1 in the Cosmos source, and XMMLSS has 4 of them detected already till date before the storm event happened. The paper is out on arXiv right now, and I'm going to also do a quick demo of the release of the catalog and web portal. So we don't stop it right there. We kind of ingested 27 different multi-wavelength catalogs in order to find out every possible multi-wavelength counterpart that is available for all these 1438 objects. This is a big list of all the information that we have, ranging from radio, from millimeter, from ALMA, infrared, ultraviolet, X-ray, gamma ray, and so basically all end up getting informations from VLAS until Fermi for all of these objects, as much as we could find. And here is just a breakdown of how this chart looks like. So we start with all the literature compilation, effectively go through the multi-wavelength cross-match, and this is our breakdown of how many sources have multi-wavelength information altogether. So this is how the sky kind of looks like of the population of the 1438 right now. So the ones that we are showing here in purple, the dark points, are the spectroscopically confirmed ones, 987 out of them, and photometric candidates of 451. So effectively, as you can see, most of them, it goes without a doubt saying that these are all covering the northern hemisphere. This is what we are lacking right now. The southern hemisphere is way, way more shallow than what we want. And this is was one of the byproducts of our exercise, that we wanted to capitalize what Rubin will be providing us that we are missing out till date. As I said, we also managed to find, we were lucky enough to find 5 objects that were in the deep drilling fields. So these are basically a zoom in effect of the Cosmos deep drilling field and the XMMLSS deep drilling field. And the stars are marking the position of the 5 candidates that are changing look AGNs. Now, quickly, I wanted to advertise you the best case scenario. This is the changing look AGN, confirmed changing look AGN with spectroscopic detection from DESI and SDSS. And all that you see is the 6-band Rubin light curves from the start of the survey in alerts from end of February until the date that we were able to observe this target visibly on 14th June. So as you can see, there is nice long-term evolution of this object throughout the filters. And if we have got 1,202 observations across the 6 channels. Of course, a little bit care should be taken on the U and Y band. That's very sparse. But what we can really see among the 4 main bands, G, R, I, C, we have a little really nice cadence coverage, ranging from intra-night up to the fact of 116 days of baseline. And so that you don't just believe my word, these are the two spectroscopic, archival spectroscopy that has been obtained earlier from DESI and SDSS. And this is something that I'm going to show you in the website that we have developed that can actually make this searching very easy for you instead of going into different websites and querying and looking for spectra altogether. So I'll take a brief moment here. I'll let you scan this QR code effectively. This is a catalog right now, and I'm going to do a quick demo of the catalog. All right, so this is the interface of the catalog itself, which basically lists down all the 1438 objects that you're seeing. These are very color-coded with the information of multi-wavelength information that they have. You can also scroll it there. There's a lot of information, 440 columns altogether, but the thing doesn't only limit yourself from this particular information. So, principle, if you want to know a little bit more about a single object, you can simply go there. It's going to query multiple catalogs, photometric catalogs. First, it looks through the DESI legacy survey imaging. And as you may know or may not know, right now, DESI is under routine shutdown from NERSC. So effectively, we do have options for fallback. So you can still get imaging for the object. And this is all interactive. So you can open this in CDS Aladdin or DESI imaging as you like. And effectively, you also have information to look forward in Simbad, NED, or Aladdin in order to get more multi-wavelength information. And something as an observer, I really like to see whether I can really use this object right now and ask for telescope time. So there's a quick, neat tool that allows you to also look at the visibility plot of the target and toggle in the dates effectively whenever you want to see that. Right now, I'm kept the capabilities limited up to Rubin Observatory's location. But in future, I do want to expand onto different observatories where you can request for time without really toggling into a different visibility plot chart. Now, other than that, you also have information about any publicly available spectra. You can query directly the link, and effectively it takes you back to the SDSS spectroscopic database. You can look at the spectra. The same thing happens for other objects which have DESI, or if you have ESO archive. So effectively, you don't need to really go through these surveys. It all is in one place platform. Any multi-wavelength information and fluxes that are available are actually listed down over here. So these are neatly organized by the tabs there. So these tabs also link you to the information listed over here in below. And any catalog metadata that's available for this object from all of these surveys that we have compiled is all listed down here neatly for you to be using for your research. Apart from that, there is a very interesting tab that we have tried to ingest. It's a duplicate checker. So this is supposed to be a community-driven pipeline. So in principle, if you do notice that your favorite object is not in the list, you can do a check very quickly here. So any volunteers for a changing look AGN, your favorite changing look AGN? All right, so I do have one, but in the meantime, you do think about it. Let's say we go for Marcadian 1018, okay? So what it does, the moment you type on the name of the target, the coordinates are accessed through CDS Simbad, and effectively you can do the search, and it will let you know whether this is already in the catalog. If it does find it, it will give you this mini link, which will take you back to the source itself, so you can see pretty much all the information that's available for this object. So, but having said that, this is not important. It's important to note that the information may be outdated, and you may have actually obtained a new epoch of spectra, and that would be useful. And you could close this one. You could actually submit an update on additional information through this information channel, and effectively this gets added on in the next version. So that helps keep things up to date as a community-driven approach. But there could be also a case where the object itself is never listed, or maybe you would like to see that, and you do a search. Effectively, this is a very well-known AGN, but doesn't classify as a changing look AGN, and it does tell you that this is not in the list itself. But nobody stops you from trying and sending a query to us. We will do a vetting and effectively see if there is actually legitimacy for this target to be a changing look AGN based on the information. We would actually ingest that into the version itself. There's also a sky map tool, which allows you to look into the objects. But for example, you can go back to your source here, any target, and you click on the show on the sky map. It actually reveals the position of this for your usability. It also helps to identify which hemisphere it's covering, so you know what instrument or facility you would like to use that. And any changing look classification previously mentioned about these objects are also mentioned over there. Now we also have an overall statistics page here. The catalog statistics are all well together here, so you can see how many sources we have. So it really helps identify if you're trying to make use of this catalog in altogether sense, how much multi-wavelength information is available across different wavelengths, and what are the statistics across different catalogs that we use for cross-matching. And finally, if you do have a new list of changing look agents, single objects, catalogs, or new objects that you have been working on, we'll be happy if you could submit on this Google form. This all gets ingested in a continuous fashion. And right now I'm trying to make it all automatic so that there's not much human intervention or any bias from human intervention, so that effectively this serves as a nice database for us going forward. And effectively with that, I'm going to stop my talk here. This is the last slide. Effectively, what we have managed to do right now is create this homogeneous kind of database right now, 1438 changing look agents, candidates, and confirmed together, of which 987 are spectroscopically confirmed and 451 photometrically candidates. The next work that we are trying to move on is to ingest the CLAS sample of about 3,000 changing look candidates that they have actually provided from the Southern Hemisphere. And this will take the whole catalog numbers to close to 4,500. So this is already starting to become really effort where we can see the numbers are really growing up together. There is a continuous development of the web portal. I'm trying to work on the mobile-friendly version coming along soon. So in case you are in commute and you would like to still check up on your favorite object, this would be also possible. And feedbacks are most welcome via Slack, or here's my email. Please reach out to us and have a look at the paper. If you have any questions, I'm happy to take it. Thank you. As a chair, one quick question.
On mine. I think that guy.
Matt, yes, please.
Yeah, this is definitely very valuable work that you're doing here, especially with Ruben coming along. Since you guys are doing this, you're really going to have to sit down hard and figure out what your definition of changing look AGN is. First of all, you got to obviously have a spectrum. You really don't know what you're dealing with. You actually have to have two spectra. One, the strict way I would say you should do this, which you're not doing, one when there's a strong broad line region, and another spectrum when it has disappeared. Actually, that's hard to do because the example you showed, the broad lines, they just got weaker. It was still the H alpha is still very broad there. So that doesn't really meet my definition of changing look. What you really mean here is, let's not call them changing look anymore. You mean strongly variable Seifert ones. Here's the problem with that slippery definition, though. We know the power spectra of Seifert ones, right? There's more and more power as you go to longer and longer timescales. I can pretty much give you any number of strongly variable Seifert ones. I'll stay away from quasar luminosities, of course, if you just let me look at them enough times for enough decades. Then it seems like almost any of them could be changing look AGN, unless you have a more serious, tighter, stricter definition of what you're going to call here, or you're just dealing with strongly variable AGN. So and this applies also to what Madison was saying as well. We got to have some serious quantitative definition here.
Thank you, Bart. I think I completely agree to your point of how different groups and different, let's say, collaborations are calling what as changing look agents. I do want to avoid that confusion. And as you can see that even with a baseline of 7,997 days, you don't see a point where actually the lines may have disappeared. This is very hard to know because we didn't have consistent photometry baseline along these epochs. So I believe that this should have been done before. Maybe we are a little bit late, but we are still getting started with this effort. And the idea is that moving forward, we should be able to capitalize on any follow-up spectroscopy information that we can get and make it more repeated. Yeah, so that's definitely, we want to do that. Thanks, Matt. All right, so moving along, the next speaker. All right, so we will have Fanzo. He's going to talk to us about the Rubin LSST deep drilling fields from multi-wavelength data to massive black hole groups.
Should I use the mic or just shout?
You can do either. I think without the mic
it
also
should
works.
work.
Okay. So, hello everyone, I'm Fanzo and I'm a postdoc at the University of Michigan. And I'm going to talk about the deep drilling fields. And actually, as Neil mentioned yesterday, the LSST AGN Science collaboration has been leading the multi-wavelength data in the deep drilling field. So that's basically the focus of this talk. I'm going to talk about the multi-wavelength data infrastructure we have built in the deep drilling fields and also how we can use that to do some science with AGN and black holes. So first of all, I should say that this is a high-level summary talk of like about 5 years of ongoing efforts. And I especially want to thank people listening here and many more. They have contributed significantly to the contents covered by this talk. And also, since we know that the DP2 is EDP2 is already there, we want to remind the community of the resources that are already there in the deep drilling fields. So we know that deep drilling fields will have higher cadence and deeper depths from LSST compared to the wide survey. And also in the deep field science, the deep drilling fields are quite complementary to the pencil beam surveys from like JWST. We know that JWST can go very, very deep, allowing us to probe the very early universe. But the problem is that it only covers a very small area of the sky. So we really need some degree scale fields to sample the cosmic volume at low redshift. So that's how LSST deep drilling fields will come in. And for these deep drilling fields, we have 5 deep drilling fields. I will primarily focus on the, I would say, classical 4 deep drilling fields. That's the Cosmos, XML, SS, CDFS, and ELISS1. And the 5th deep drilling field is the Euclid Deep Field South that was finalized only very recently in 2022 March, I think. So in this 50 deep drilling field, we don't have time to prepare the multi-wavelength data, so we kind of leave it to the future. But for the other 4, we already have lots of multi-wavelength data from X-ray to radio, and we know that AGN is really a multi-wavelength object. For example, the Cosmos is a very famous field. People have done a lot of work in compiling the data there. We have Cosmos 2015, 2020, and the 2025 catalogs in Cosmos. And for the other 3 fields, CDFS, ELISS1, and XML-SS, we have also compiled and reduced the X-ray to radio photometry in these works, and we eventually end up with a catalog with 3 million sources covering the central part of the deep drilling fields. We are not able to cover the whole deep drilling field because the outer part of these fields do not have quality multi-wavelength data. But we are able to do that within the central, like 40% of the area. And for these sources, we have done very careful analysis. I mean, source classifications and photometric redshift measurements, and also spectral energy distribution feeding, etc. So this plot showed an SED feeding results of an X-ray AGN. So the basic idea is that if you have some interesting sources in the LSST deep drilling fields, not necessarily AGN, but can be anything, you probably could just check our catalog. We have already provided all the information we have, including photometry, photometric redshifts, and the properties, etc. So that could be a very good resource for the community. And we also have done careful AGN selections in the deep drilling fields, including X-ray, medium-thread SED, and a radio selection method. And of course, LSST, we are enable like variability selection methods. So the basic idea is that we can have multiple methods, allowing us to build an AGN sample as complete as possible and also as reliable as possible. So that's the data side. And based on this multi-wavelength data, we have scientific investigations. I'm just giving one example that I've done with the black hole growth. So this shows the basic picture of the black hole, the evolution of the black hole population. We have some early black holes that then they can grow through accretion and mergers to become the supermassive black holes we see today, and some of them may have gone very little growth, and they became the so-called leftover intermediate mass black holes. Although I want to say that I'm increasingly skeptical about the term leftover intermediate mass black hole, but that's another story. I will leave that to offline chats. We want to like quantify this whole picture, how the black holes grow, and we have these surveys, and to quantify the whole picture, we need lots of surveys. These surveys for the wedding cake design, we have deep pencil beam surveys from for example, Hubble, JRC, etc. And the plot here shows the accurate depth versus the solid angle. So the deepest layer is from, for example, Candle's survey, and the LSSC deep brilliant fields is a very important part of the median layer. So that's why LSSC deep brilliant fields are important. And of course, we have wider area surveys. So with all of these surveys that can provide complementary information, we can really measure the black hole growth rate. Here I'm showing the m dot, basically the dm over dt, averaged over the whole galaxy population, including both AGNs and also inactive galaxies. And they are averaged so that they are in a cosmological timescale sense. And the AGN variability and AGN duty cycle have all been averaged out. So this is really just a mean value. And here I'm showing the black hole mass growth rate versus the stellar mass for massive galaxies, and you can see it evolved with redshift. And in our recent work, we also have extended that to the low mass galaxies. So combining this, we can map the black hole growth continuously for the most massive galaxies, like from like 10 to 12 solar mass down to very low mass galaxies, so from like 10 to 7.5 solar mass. So that's like 4.5 orders of magnitude. And we have done that across the vast majority of cosmic time. And we have done beyond that. It's not, we also calculate the specific accretion rate distribution, which is just a proxy of adequacy ratio distribution, and also some other related quantities. And this work can help you define the AGN population that we would expect. And indeed, it has been directly fed into the LST simulation of AGNs. From this work, you can check this from an in-kind contribution team called Agile. And in principle, we could also extend that down to the low mass regime, but this could be left for the future. I will skip that. But so by now, we are having DP2, and we are still continuing to improve the data infrastructure in the deep brilliant fields. And for this purpose, I want to highlight the DDF ELISIS-1 field is not as famous as Cosmos, but it's still a very important deep brilliant field. And you can, this is the TP2 visits and night from LSST. You can see that the ELISIS-1 has the highest number of visits and also nights. The comparable one would be Cosmos. They both have like over 700 visits, but the Cosmos time span is very short. So if you want to do like AGN variability, then ELISIS-1 is still the best. So the problem is that ELISIS-1 have very, very limited spectroscopic data. Only 70% of known AGNs there have spectroscopic redshifts. And actually half of these spectroscopic redshifts are from very low resolution Grisant spectrum. The spectral resolution power is only like 30. So it's not really useful other than just giving you some redshifts. And we know that photometric redshifts for AGN are also very difficult. So we want to improve that. So we have been doing an AGN spectroscopy survey with Magellan using the institutional time at the University of Michigan. And you can see the footprint here. And our observation is already ongoing. It will be finished in mid-October. So we have selected most of the known AGNs identified from multiple methods like X-ray, medium thread, SED, and radio, etc. So if we are working on like AGNs in ELISIS-1, it's very likely that your AGNs will be targeted by our survey. So you should just check with us. And here I'm just showing some examples. So this is the real plate we have used at the Magellan, and this is the example spectrum we obtained. We are still working on the data reduction. It's been partially reduced. It's a little bit hard because this instrument has no pipeline, so we have to do everything from scratch. but we're working on that. So we aim to have the spectral ready this fall and at least no later than early next year, so that we can provide spectroscopy information for AGNs in the ELYSIS one, so that we can have synergy with LSST DP2. And again, if you have found some interesting targets, you can just check with us, and our observations will be finished in mid-October this year. So that's that. And lastly, I want to say that we are there's something different that in the AGN Science collaboration, we actually have a dwarf AGN task force. We have a bunch of people interested in dwarf AGNs, in very low mass galaxies, in the medium mass black holes, etc. So we recently have launched a dwarf AGN task force in late 2025. We aim to work on dwarf AGNs with LSST in a collaborative way, and we have had several meetings this spring. And if you're interested, just send us an email to Colin Berg or me, or just talk to me, and we have a Slack channel related to that. And I will stop here, and I'm happy to take any questions.
We have time for one quick question.
You tantalized us with that terrific black hole growth graphs that you have. Did you have to make some assumption about accretion duty cycle, and did it depend on luminosity?
No, so duty cycle is actually part of the output of this measurement. So we do have some assumptions. We assume that the accretion rate distribution follows the double power law, which makes sense because the actual luminosity function follows the double power law, and we assume that it evolves continuously with stellar mass and redshift. So that's the main assumption we have adopted.
Great. Let's thanks Fang again. Our next speaker is Kendall, and we're going to hear about wandering black holes. Okay. Thanks. All right.
Hey, everyone. My name is Kendall Sippy. I'm a PhD student at Penn State University, also working with Charlotte Ward. And today I'm going to tell you a little bit about how we're searching for wandering massive black holes, MBHs, using LST data. So, what is a wandering massive black hole? Why do we care about them? So basically, the sort of idea of how massive black holes merge and grow is that there would be a galaxy merger. The two central black holes from the galaxies kind of spiral in. They eventually merge with each other. And then through some nebulous process, we don't totally understand, this leads to AGN galaxy coevolution. However, that's kind of a simplified vision of this, and we know that not every galaxy merger will lead to a successful massive black hole merger, and especially in cases where you might be having a minor merger where the dwarf galaxy hosts like an intermediate mass black hole, that intermediate mass black hole could potentially get stuck wandering around the outskirts of the larger galaxy for long timescales, long enough that we might be able to see them. And indeed we have. This is from Yao et al. 2025. This is an offset tidal disruption event. So this yellow part is the galaxy, and the little, blue dot is a intermediate mass black hole that experienced a tidal disruption event. And there have been about 6 or so of these that have been found so far. And simulations, once you stop artificially pinning massive black holes to the center of galaxies, you actually find that lots of these things should exist. And that's shown on the right. This is from the Romulus 25 simulations by Riccardi et al. 2021. And this is an example galaxy they found in their simulations that, so all the little black dots are like massive black holes. And then on the right is an X-ray simulated image. So this galaxy actually has 5 AGNs in it. So basically the question is, where are these things in real life, right? And I mentioned we found some as tidal disruption events so far, but the AGN question, whether that can be a wandering AGN, the jury's still kind of out on this. So this is what I'm trying to figure out. So to do that, Maddie talked a bit about this in her talk. We're using scene modeling with Scarlet 2. So Scarlet 2 does multi-resolution forward modeling of images. It has non-parametric galaxy morphology models and all this other great stuff. And we can model variable sources, which is important for what I'm doing because I'm using the variability of these AGNs in the LSST data in order to get positions for them that are independent of the light of the host galaxy or anything else, just based on the variability. So this is an example model, observation, residual here, and you can see this is actually Euclid near infrared data, and we can completely handle this crazy correlated noise that's going on and model this scene with 30-some objects with non-parametric shapes in it. So this is sort of my methodology, the idea of my methodology that I've been developing. So basically, we have in the Scarlet 2 scene a non-parametric host model, which is not just the galaxy, but also the static component of the AGN light. So however bright the AGN is in each band at its faintest, basically. And then there's the variable component of the AGN light, which is very faint, like 23rd, 24th magnitude variability that's occurring. And that is a separate point source in the model. And the idea behind this is if you're using imaging alone and not using the time domain aspect, if your center of your galaxy and your AGN aren't in the same place, you actually have no good way to tell that. So this left example is kind of an extreme diagram of what an offset AGN could look like. So things that are in white are things that are actual properties of the galaxy, and the colorful markers there are things we can measure. So we can't, if the AGN in the center of the galaxy based on starlight aren't in the same place, we can't measure that, but we can measure the centroid of this host, which is kind of like a weighted average between the two positions. And we can measure exactly where the AGN is because we can measure where this variable point source is. So we can measure the offset between a variable point source and the host centroid as a proxy for measuring the distance between the AGN and the center of the galaxy. And on the right here, this is like a normal regular galaxy where all of these things would be in exactly the same place. Okay. So basically the plan for this project is first to develop the Scarlet 2 modeling methodology using a control sample of just regular old AGNs that live in the middle of their galaxies to make sure that the method isn't, spuriously finding that every single galaxy has an offset AGN. And then once we start getting prompt products with the LSST transient alerts, we're gonna start searching for actual candidates, model those galaxies and their environments with Scarlet 2, from which we can retrieve independent likers for the AGN, position for the AGN, photometry for the host galaxy, and morphology models, and then hopefully eventually build a catalog of these sources. So for the rest of this talk, I'm mostly going to be talking about the work I've done building this modeling methodology on my control sample of regular AGNs. So this is sort of just to emphasize kind of the need for non-parametric galaxy morphology models. I am doing joint analysis of Euclid and Rubin data. And once you have this space-based resolution, as you can see in these Euclid images here, surface profiles don't cut it. You can't model this with a surface profile. So you can see the non-parametric morphology models are doing a good job matching that. And they can also, if the shape is actually pretty surface-like, as you can see on the lower right, they still can reproduce that as well. Another thing I've been implementing is 2-component host models. So basically, because Euclid has these near-infrared bands, the morphology of the galaxy changes a bit as you go into the near-infrared, just because you're probing, there might be dust, you're probing like different stellar populations. So I've been modeling the galaxies with 2 extended components on top of each other that kind of allows it to adjust the near-infrared. you can see, so these panels are like the model scaled down to the flux of the galaxy in the image. So that, like, the center panel is like what would be subtracted from the data in a residual. And then the right one is the actual images. So Euclid visband, NIRY is like the closest one to visible light. And then we're going further into the near infrared. So you can see NIRY and J look pretty close to the morphology model in visible light, but once we get out to NIRH, which is like 1.5, 2 microns, it actually looks pretty different, and it still has this kind of funky butterfly shape going on. So we do need that extra component there. And this is just another example of the same thing. So the left plots here are data, and the right residuals from a model for a different galaxy. See, this is the Rubin I-band from DP1 data. Looks fine. This is Euclid NIRH. Residual does not look fine. Then if we add another component, the I-band still looks fine. And now the NIRH looks much better as well. Okay, another thing we had to implement was astrometric shifts. So sometimes there are systematic differences in the WCS between the Euclid and the LSST data, which creates these dipoles. So you can see the upper left panels in the residuals, it's dark on the left and bright on the right. And then in the Euclid image over here, it's bright on the left and dark on the right. So it's because the model's trying to fit simultaneously two different images that are slightly not aligned with each other. So we can fit a WCS shift, and that fixes the issue here. We can also recover photometry of the host galaxy to understand what the host of the AGN is like. So this is just showing the LSST bands and the Euclid bands. We recover the red points are the photometric spectrum that Scarlet 2 recovered for this galaxy. And this one also happens to have two little satellites, so we can model those separately and completely decompose them from the main galaxy and get 3 separate spectra to understand the properties of those as well. Yeah. Okay, and then more on the AGN side, we can recover independently, just straight from the imaging data, these variability light curves. So the left one is the one from the Scarlet 2 model, and the right light curve here is like straight from the LSST catalog. You can see we basically recovered the same shape. There's a bit of a systematic offset in the redder bands where Scarlet 2 is a bit brighter. That's because we're summing up the flux of the whole galaxy plus the variable component of the AGN. We aren't doing like whereas this one is like a PSF force photometry. So we're getting a little bit more of the low surface brightness extended parts of the galaxy, and that's making it a little brighter than over here, but otherwise there's good agreement. And lastly, and possibly most importantly for my work, we can, as I mentioned earlier, independently measure the centroid of your galaxy and the position of your variable point source, which is your AGN. So these are just 3 different galaxy models in my control sample. The blue X's are the centroids. We have to use centroids and not centers because it's no longer a surface profile. It doesn't have a center. So the centroid is just like a weighted average of the brightness of the whole thing. You can see they look like, when you look at them, they're in the place where you would think they should be. So that's nice. And then we get AGN positions as well. And you can see they're pretty close to the middles of the galaxy. We do get a bit of scatter, especially with the AGNs, where the amplitude of the variability is smaller than sort of the error bars are getting larger there. But yeah, this is the control sample. So we want them to be in the middle of the galaxy. So this is good. And yeah, that's my summary slide. And I'll leave it there. Thank you.
I will quickly go first, the in-person question.
Thank you for an interesting talk. So for a technical question about how you define those centroids,
the variable component is the thing that you're going to measure the position of the AGN, but there will be also a baseline flux. Is that going to contribute to the host galaxy, as it were, the point source that is not the variable component?
Yeah, so basically.
I mean, and is that going to bias you? Yeah.
Yeah, in order to avoid that issue, I'm kind of just letting that happen. So basically, like the centroid, I'm viewing as not being an independent measurement of the galaxy without an AGN.
Mhm.
I'm just viewing it as being a weighted average between where the center of the galaxy may be and where the AGN is, which may not be the same place.
Okay.
So actually, it's better if I go back to my kind of blobs.
Yeah.
So the centroid, we aren't assuming that necessarily indicates where the center of the starlight of the galaxy is. So in order to measure the difference between where this white point is and that one is, we're actually measuring the distance between here and here.
Yeah.
Yeah.
No, I understand.
Yeah, as a proxy for that.
We do have 2 online questions, but we are running out of time. May I ask Matt and Thaisa to write it on Slack, the questions for Kendall? That'd be great.
Or
Thank
you
you.
can just send me an email too,
Okay,
because
yeah,
I
yeah.
couldn't get on the Slack. Here's my email's there. Okay.
Wonderful. Thanks. Let's thank Kendall again. And for our last speaker, we have Gloria. And she is going to talk to us about characterizing known agents in the Rubin data preview. Take it away. Good.
Hello.
Yeah.
Can you hear me? It's switched off.
Yeah, but I can't hear you properly.
I'm very quiet. Okay. Hello. So I sent this abstract before the DP2 release was announced. So I quickly changed to an initial look at AGN in the early DP2. This is definitely very initial work. Also, I should say, so I'm Gloria Fonseca Alvarez. I am a postdoc at NSF NOR Lab. I specifically work with the Rubin Observatory operations team. So you probably have all heard this, but I just wanted to show it. So last year, we released the data preview 1, which was based on commissioning data from the LSST ComCam. This was about a few months of data for only 7 very small fields, where it did include a couple of the deep drilling fields, and the extended Chandra field south was the most observed field. So there was some time domain data, but unfortunately not like the most useful for AGN. Now on Monday, we got the early data preview 2, and it's early because there will be another the full release will come later this year, but what's coming out later is just like the visit images. The catalogs are already available. And so this is based on LSST camera commissioning data from April to September of last year, and then also some early optimization data from earlier this year, where LIE's S1 and Cosmos were heavily observed. So these 2 data previews are very different. There's like very little overlap between the EDP2 and the DP1. Some of them, the fields do overlap. But the DP1 was very short, but there were a lot of observations per night. And the DP2, there is a longer baseline and a greater area. However, it's still not quite the same survey strategy that we will have in the future. So I am working with a few, right now, a very small sample of external known AGN. So I'm working with samples from the DESI data release 1. I'm also using galaxies and stars, which I will use for comparison to quasars. I'm also using data from the Euclid quick data release 1, which other people have already given wonderful talks about why we should care about data from Euclid. I am using specifically a sample from Yang et al. 2025 that looked at 3,500, I think, as far as I know, they are spectroscopically confirmed. And I'm also using the quasar catalog, which is a compilation from the literature. So what I'm showing here is essentially I've cross-matched these catalogs to both the DP1 and the DP2 catalogs. And I'm just showing a little map that shows the overlap. You can't really see it, but in red is things that have matches to the DP1 only. So you'll see that there are some fields that do have only DP1 data. And there's a lot of matches for the DP2. I think a lot of these in this little area are from DESI. Also, I forgot to mention, this little stripe is supposed to be sort of like the wide, fast, deep. And then you also have your deep drilling fields, and you have a bunch of small fields that are that were like from first look. But there are two main catalogs that I am matching to. One of them is the object catalog, which are things that were detected in the co-added images. And then there's the difference image analysis catalogs, which give you things that were detected in difference images. So for the things that were detected in the difference imaging, I am looking at their light curve, since at least that gives us some indication that they might be variable. But so I'm just showing an example AGN that everybody just kept finding it in the data, in the DP1 data. It is a quasar that is already known. And if you can see here, the DP1 light curve is very, very short. For comparison, I have here ZTF, and I did a terrible job of showing it, but you can see here what the DP1 data looks like, which is just like a tiny bit of the, the multi-year ZTF data. But here on the right is what that same quasar looks like in the early data preview 2. And I screenshotted this from the one of the CST tutorials that myself and the community science team worked on. But you can see that you can actually you can see variability. You have a decent amount of time as well. So next up, I just wanted to show you some example light curves. Like Fan was just saying, LA's is one of the most, is going to be a really important one for the DP2. So this just from visual inspection, I was looking at things that had a lot of detections in the difference images. And I found this AGN. And you can see it varied quite a bit. So I also looked at the for the ones that I noticed were somewhat interesting. I looked at their light curves in Antares to see if there was any additional data. So I'm not quite sure about the exact dates, but as you can see the little rice here, and there's some data that came after the data that went into the DP2. And then another one, this one is not as variable as the other one, but you can see that it also has some additional data after the DP2. And then I just wanted to show an example for Cosmos. Like Fan said, it is a very popular field, but however, we don't have, like the observations were very short. But yeah, so this is what you might expect an AGN light curve to look like in Cosmos in the DP2. And as you can see, it has a lot more observations from the past. The other catalog that I was matching to was the object catalog. So that one came from the deep coad. So the positions are different than the ones from the light curves, but I did cross match them and I found a lot more matches to that. But I'm just showing here, like, your basic plots of like magnitude versus redshift and your color diagrams. So one thing that I'm interested in doing is providing recommendations for the community, because the LSST catalogs have a lot of different measurements. One of them is, the force photometry, which is only all of the light curves are only in force photometry, which is only PSF photometry. And then there are also other flux measurements like aperture fluxes that are available from things like from like this different table. So I'm trying to see if for any kind of AGN, if it would be preferable to use not the PSF photometry. But this is all just like very initial work. But that's what's just one of the things that I'm going to be looking at. So again, my goal is to characterize known AGN in the currently available Rubin data previews and provide recommendations for the community. I've so far identified about 300,000 objects at the locations of known AGN from DESI, Euclid, and the literature. There are only 45,000 unique DA objects, so I'm only looking at that many light curves. And I'm planning to expand the AGN catalogs that I'm using, including, for example, the work that Fan and everybody else has been doing with XMM serves, I think it's called. And I'm also going to try to characterize the variability and also look at their photometric redshifts, which are already available. But that's it.
Any questions for Gloria? I hope they're being up.
I just run that.
Yeah.
An interesting thing to do might be to divide the sample into type 1s and type 2s and explore that. I don't know if your definition of AGN includes Seifert-2s and other such things.
Yeah, I'm using AGN very loosely. I'm mostly looking at quasars. For right now, I want to be like absolutely sure,
Great. So we still have a couple of minutes. So just wanted to shout out if anybody has questions for all of our speakers. We can have a couple of them now. Or else I would like to highlight again that on Slack channel, you can always reach out to all the speakers. And the channel is active on there. So please feel free to browse through the channel. And feel free if you're interested. Thaisa, yes, please go ahead.
Yes. Hi. Thanks for all the presentations. Very nice. I would like to know which is the difference, if somebody can answer, between the images of Euclid and the images from Rubin, comparison of these images. Of course, I know Euclid is outside the atmosphere, should be better, but do we have a number or something? How better are Euclid? Because it's a smaller telescope, so all these aspects. I don't know who can answer this.
Oh. I'm just looking if there is anyone on.
Very quickly, because I did not compare them directly. So
Okay.
the resolution, first of all, and also Euclid is from space, so it has a better resolution in the optical images, but a larger filter in the optical range. And the PSF, the magnitude limit should be more or less compatible, because I think that Euclid declared something like 24.5 magnitude limit, but is defined a little bit different from an LSST. So yeah, especially if you're looking at the environments, it should be better if you want to look at possibly blended sources, as the previous talk were showing. I don't know if some of the students working with Charlotte would want to add something.
Yeah, I think.
I think the camera might pick it up.
Okay, thank you. I think, LSST is a lot deeper with a single exposure. I think Euclid's goal is to reach 24.5 magnitudes, but that's in coads. LSST can get deeper than that in a single exposure. And Euclid is mainly producing, at least currently, coads, whereas LSST has the time to main element that can be important. And also the difference in the PSF is really large, as some of the other talks showed, because LSST is nominally 0.2 arc seconds, but really it's more like 1 arc second with the seeing. Yeah. whereas Euclid is 0.1, actually.
Okay.
Yeah.
Okay. Yeah.
So
Okay.
thanks, Thaisa, for the question. Let's
Okay, thank you.
give a round of applause for every speaker for the session. We are adjourned. Have a good rest of your day. Thank you.